you for joining us today to our latest canonical webinar. While we are waiting for everyone to join in, we will start quickly in the next 30 seconds. All right, let's get started. I'll pass it on to Ijal, who will be our speaker today.
Thank you, and welcome everybody. Thank you for taking the time to join this webinar. My name is Ijla Lotfi. I am with Canonical. I've been with Canonical for almost 3 years now. And today I would like us to discuss the topic of defense in depth. Specifically, how does Ubuntu think about it, and how you can also start to think about it for your own organization. So this is a funny picture, but it very much speaks to the reasons why I wanted to host this webinar, which is that as an organization or just a normal user, when it is time for you to pick the security solutions and primitives that you want to adopt in order to better secure your estate, it's honestly like a buffet. It's just a lot of choice. Everybody claims they are the tastiest, best solution. And it feels sometimes that users are just picking and filling their plates up with every possible security solution. And that's not good for more than one reason. And to be frank with you, we almost feel like that as well. Obviously, we do release Ubuntu regularly. Every 6 months, we put out a new Ubuntu. And before that, there is a lot which goes in the background in which where we have to think about what are the best security primitives that we want to implement and support for every particular version. And the same for us. We feel that we are confronted with the buffet of security solutions, and we need a way to cut across the noise and offer the right, most optimal set of security solutions. So I want to give you insights in the rest of this presentation about how it is that we think about when we make those choices. And you would assume, and I would understand your assumption, that when we make those choices, we keep the end user in mind. Like it is the end user's requirements, and we define them, and then we work backwards and we pick the solution. Yes and no. Yes, end users are important, but in cybersecurity, the attackers and the capabilities of attackers are realistically what is driving the choices we make about the security primitives we adopt. Attackers are driving cybersecurity. So I can hear some of you already thinking, well, these OS vendors, they're just thinking about attackers and they have given up on perfect security. If it was, some serious cryptography researcher, they would go about this much more rigorously. Well, some people did very early in the 19th century. One of them was Claude Shannon. And he came up with the one-time perfectly secure algorithm. And it is also a very simple one. It just requires the following. For every plain text, the encryption key is assumed to be truly random. It is assumed to be of the same size of or more of the plain text. You are expected to not reuse that encryption key ever. It's a one-time use key. And finally, you are just expected to somehow manage the key distribution. So if you can satisfy all of these 4 requirements, then yes, you will have your theoretically unbreakable encryption key. You will have perfect secrecy. I don't have to tell you that all of those 4 are extremely difficult to achieve. They are impossible in practice. And one-time pad is just a theoretical scheme that we learn about at university, but it is not really at use at scale in any commercially viable application or setting. So what we want instead in security is not perfect secrecy. We don't want perfect security. What we are looking after actually is a theoretically breakable cipher. Yes, I want, for example, an encryption cipher that I can break, but there is some nuance here about the breakability option, the feature. I don't want just to know that it can break. I want a cipher that I know precisely how and when it can break. I want to know the boundaries of when this cipher is reliable, and I want to know beyond which boundaries it becomes insecure. For example, what is the computational power that I can assume about an adversary for me to trust that this is secure? If I assume that somebody has a quantum computer, that's an assumption that I'm making about the attacker, and it would, for example, make many of the symmetric encryption schemes that rely on today and consider secure, it will make them insecure. So effectively, what I'm saying is the reality of cybersecurity is that things and systems are secure precisely because we understand how and when they break. And that's what we can refer to as computational security versus the theoretically perfect security that I spoke about in the one-time pad, for example. So the way we think about protecting Ubuntu systems at Canonical is it almost feels like we are playing a chess game and we're playing it against an unknown player. And what I mean here is not just an unknown player that I don't know how they are going to move, like it is the case in traditional chess games. No, truly here the unknown is unexpected in the following ways. When I'm playing another human in a chess game, I don't expect that they're just gonna have three hands suddenly and they're gonna start making moves with three hands. But in cybersecurity, usually the assumptions that break our security guarantees are so unexpected. You could remember, for example, the Spectre meltdown and how suddenly we learned that side channel attacks can be very precise and they can go right and they can allow somebody to actually break the entire security guarantees of both the kernel and the user applications that run on the system. So this is how fun, how challenging, and how exciting the cybersecurity game that we're playing. Now, let's play. That's all we're gonna do in the rest of this presentation. We're gonna make an assumption about who our attacker is, and then we're gonna see the security primitive that you can use and that Ubuntu implements in order to counter the potential attacks of that hypothetical attacker. The first one, and this is really the lowest, the weakest level of an attacker that you can assume. This is just somebody who will leverage known vulnerabilities. So they will not try to find some fancy 0 days. They will just wait until actually there is a CVE assigned to a vulnerability. They will wait until people would disclose how the exploit looks like for this. Maybe they will wait even for the exploit to be automated. They will acquire those attacking automation tools, and then they will hit their targets. Now you will tell me if this is a known vulnerability, how serious of a threat it is, because surely enough people, if they see a CVE, especially if it's higher critical, they would just patch. They would just patch their systems, and this is potentially an attacker I wouldn't have to worry much about. So I'm going to ask you, how many organizations patch known disclosed vulnerabilities? Let's be generous, even after 2 months after their disclosure. Please give it a guess, and I'll be curious to see, the answers that you share with me on the chat window. I think you can have an icon for that on the side of the Bright Talk or whatever you're watching the webinar. Just type me a number. And if it is anywhere close to 24%, then yes, congratulations, you got it right. It's only 1 out of 4 organizations which managed to patch a known vulnerability after 2 months. The rest, I don't think I want to. I don't want to guess. I don't want to know. to be fair to these people, it is not because they are necessarily lazy or necessarily because they want to expose intentionally their organizations or their platforms to vulnerabilities. It's just because realistically, fixing software vulnerabilities is difficult. Um, the average open source project, for example, has around 69 dependencies. And this has made it so that on average, it takes around 100 days, precisely around 98 days, for an organization to fix a vulnerability. I think this is unacceptable. 98 days is unacceptable, especially when the CVE, the vulnerability, is publicly known and the fix is available for it. And we certainly should be able to do better. So that's a challenge that Canonical and Ubuntu we put for ourselves. And then we said we want every Ubuntu user to be able to patch all high and critical CVEs within an average of 24 hours. I can tell you that usually it is less than 24 hours because we do work directly with project communities and with vendors, and we know about a vulnerability before it is public, and we're able to provide a patch before it is made public. But let's say we give you a vulnerability fix within 24 hours. That's way better than 100 days. And we're able to provide these fixes thanks to, if you're running any Ubuntu, whatever you run it, you'll be able to consume a subscription on top of Ubuntu called Ubuntu Pro. It is available for free for all personal users and for small business users up to 5 machines. If you're an enterprise user, this is an enterprise feature that you pay for. But whatever your use case, what Ubuntu Pro gives you is the following. So what you see on the left side of this screen is, let's say you are on Ubuntu 20.04, which is an LTS, long-term supported Ubuntu version. And then, of course, you will be supported as usual. You will continue to be supported for 5 years. And the security fixes are going to still be available for all 22,300 packages that are part of our main repository. Now, if you do activate Ubuntu Pro, what you get is both a vertical and horizontal expansion of the added value of security fixes. So the years increase to up to 12 years of support. So if you are one of those organizations that really care about stability, if you are running Ubuntu as a host OS, then I know that it matters that you don't have to upgrade your Ubuntu every couple of years. And 12 years is a sweet spot that we see for a lot of the people who use Ubuntu at an enterprise level. But you also expand the value vertically because we do not only support the 2,300 main packages, but we also support the universe repository, and that's around it's more than 20,000 packages and growing. So the fact that Canonical is the one that makes sure that makes possible Ubuntu Pro, it's great because we know intimately the distribution. We are the publisher of the distribution, so we're able to do very rigorous regression testing for the fixes that we put out, so that there is minimal risk of a fix breaking and breaking your platform. And then people can choose whether they want support or not. And we take API stability also very seriously when you do fix CVEs. One thing which I noticed goes unnoticed when we talk about security fixes is that, yes, upstream project, let's take here the example of OpenSSL. Upstream projects do release LTSs for their projects, and they do provide security fixes for those LTSs for some period of time. Each project has its LTS period, but people stay on OSs for much longer. And once OpenSSL, for example, goes into end of life, the maintainers of the project will not be security maintaining that particular version. They will be jumping next to the next LTS version, and that's the only one they will provide security maintenance for. But we think it's very important that the Ubuntu users continue to get security support for the version that they have chosen with the Ubuntu that they have chosen. So every new fix that comes to a newer OpenSSL version, even if the previous one is not supported, the canonical engineering team working on this, they will make sure that it is backported to your version and it is tested. And yeah, that's how we ensure that you continue to be supported for up to 12 years. So backporting is a huge part of the workload that we do in order to ensure long-term security maintenance. If you are currently on an Ubuntu laptop, if you're watching this from your Ubuntu, you can type quickly a pro security status command so that you can see pretty much the breakdown of the packages that you're using from main, from universe packages. And then you can also see if there are any CVEs which you would benefit, which are currently not fixed, or if there are any services that you have not enabled in Ubuntu Pro. So please make use of this Pro status and Pro security status. This is an overview of a comparison of the number of security maintenance, security patches, or the packages that you would be able to maintain long term with or without Ubuntu Pro. I know a lot of people care about Python packages, Node.js as well, but yeah, you can pinpoint here and you can assess the risk that you want to take for your organization, depending on how your estate looks like. Okay, so that was the first type of attacker that we protect ourselves against. They're just, weak-ish. They just exploit known vulnerabilities. But I want to take us here into a slightly more sophisticated attacker class. Somebody who will go after the implementation of cryptographic algorithm and try to break their implementation versus brute force the key or something like that. So these people don't want to crack the encryption outright. They just would like to use some sophisticated techniques like padding oracle attacks on improperly implemented encryption schemes. And it is really important for enterprises and individuals here to avoid applications that use unvalidated cryptographic modules or cryptographic libraries in ways that do not perform with the expected security policies. And implementing cryptography is a very subtle business. So that's why we don't go about it alone. When we certify our kernels, our Ubuntu kernels, for cryptographic conformance, we rely on the Federal Information Processing Standards, short referred to as FIPS for short. The people who in the US and the government sector would be very familiar with this because it is the standard in US non-military government agencies. And it is also by extension the standard for the contractors who work with these agencies. And you would be able to consume FIPS under the same subscription umbrella with Ubuntu Pro. So I showed you earlier the second command, which tells you which particular services under Pro you are consuming and which you need to enable. So extended security maintenance was one of them, and FIPS compliance is another one. So there are several FIPS components that we certify. There is obviously the Linux kernel. There is OpenSSH CLI, OpenSSL, libgcrypt, and strong swan. This effort has started all the way back in 1804, and it continues certainly to 2404. Yeah, this is just a reminder of the pro status command for you to check if you're consuming FIPS. And that also brings us to level 2 of this game, if you want to look at it that way. We now can look and turn our attention to an even more sophisticated type of attacker. This one is actually going to go after your particular configuration of the system you are running. So, and if they're going to go after configuration, it means that the way to protect yourself against this type of attacker is by hardening the configuration itself. You need, for example, to tighten the default settings. If there are components which are unnecessary, then remove them. In that way, you would be shrinking the attack vector or the surface attack. You want definitely to configure login and integrity checks. You want to enforce encryption, for example, by using full disk encryption. And you definitely want to still keep on the good practices of keeping patched and up-to-date software that is running on your platform. I'm going to go into further details of how these look like specifically for Ubuntu and how they are implemented in a bit. But the standards that we follow for Ubuntu are both DISA-STIC and CIS benchmarks. DISA specifically, DISA is a combat support agency. It's part of the DoD, and it follows the security technical implementation guides that are based on NIST recommendations. And for CIS, the Center for Internet Security, it provides CIS benchmarks, and they have become very widely adopted across the industry, and so much so that we have decided to provide for Ubuntu users a tool that allows them to automate the auditing of their systems, so that they know in which ways they are compliant with CIS benchmarks and in which ways they are not. And we automate the auditing, and we automate the application of the hardening policies to an Ubuntu system. What do I want to highlight here? Yeah, that this tool is available starting Ubuntu 20.04 LTS. It is also available in 22.04. Prior to that, we did have hardening, but we had separate tools for both for CIS tools. But the USG, the Ubuntu Security Guide, is relevant for both DISA-STIC and CIS as well. It is a command line utility. It can automate your compliance auditing as well as apply remediation, and you can tailor actually the profile of the hardening that you want to audit or apply to your system. So it's flexible, and it's easy to use. These are the commands that you would want to use if you want to enable USG as part of Ubuntu Pro, first of all, and then if you want, then install it and then audit your system for DISA-STIC compliance or CIS. This is a bit more details about some examples of the most commonly applied hardening configurations. For example, disabling unused USB ports. Specifically, if the server does not need to use a certain hardware feature like USBs, by leaving them enabled, these can often, it just increases the surface of attack, and you can actually disable them in BIOS in order to even prevent further physical attacks against the platform that has this enabled otherwise. We also see a lot of people making use of the policy of removing unnecessary unused components. At the end of the day, Linux OS is really, it covers a lot of packages, and not everybody is going to need all of those packages. So bring things down to the minimum that you are using, again, because it reduces the attack surface. Login and integrity checks. So all systems and application logs should be stored on a remote server, and this way you can ensure that if there is an attack, then the attacker will not be able to delete the logs and cover the tracks. And file integrity monitoring software should be deployed to provide warnings if any unexpected changes occur, which might be indicative of an attack. So these 4 measures are the types of hardening measures that you can take audit for or apply as part of the USG tool. Okay, so far so good. We have seen 3 types of attackers, but we know that there are smarter people out there, much more determined attackers, who would put in the effort, time and money in order to actually find zero-day vulnerabilities and exploit them before they are made public. So of course this is not possible for every type of attacker, but there are a lot of people with the resources and the motivation to pursue them for whatever reason. So for those, for example, let's say they will go after trying to find a zero-day vulnerability within Firefox. And then if they do that, then the goal for them would be that they will use that vulnerability to gain unauthorized access to some IO devices in the system, or to some files that they wouldn't have otherwise access to, or to just move laterally within the system. So for us, the way we at Ubuntu think about protecting ourselves from this is through mandatory access control. There are a number of Mac modules available for Linux systems. The one that we find the most effective for confinement is AppArmor. It's very easy to use. We use it to build profiles for a lot of applications that we ship by default for Ubuntu. And it is a very effective way to contain an exploit. So yes, an application can be exploited if there is. AppArmor will not make a Firefox buffer overflow go away. No, but it will prevent an attacker who potentially would exploit that buffer overflow from moving laterally. If they want, for example, to, I don't know, gain access to your network, they will be denied unless you prove that. So yeah, think of it as an isolation confinement technology, and that's how we address the type of attackers who go after 0 days. As I mentioned, there are a bunch of pre-installed profiles, AppArmor profiles for the applications that we think need the most and which are used most by our Ubuntu users. But if you do have a workload that you consider to be critical and you do not find that we ship an Ubuntu AppArmor profile with it by default, then there is a tutorial on our website that will guide you into how you can create a profile yourself and attach it to that workload. It's pretty straightforward. But just to give you an idea about why is it straightforward, it's because AppArmor has a complaint mode. So you can, for example, for an application that doesn't have AppArmor profile, you can activate complaint mode, and that will um, kind of capture all the actions that the program is trying to do. And that should give you an idea about the baseline of what a good behavior for that particular workload looks like. And you can use the results of the complaint mode in order to build the profile. And anytime the application would try to deviate from that baseline of good behavior, then AppArmor will prevent that action from happening, because it will assume that it is coming from a malicious from a vulnerability that has been exploited within the application confined by the AppArmor profile. Okay, so far so good. We are also able to find in Ubuntu a primitive that gives us the ability to prevent 0 days vulnerabilities from being escalated. But what about somebody who is even more determined? Like, there is an attacker who, and this is the funny thing about cybersecurity, honestly, because attackers are, well, you can call them lazy, but you can also call them, economically savvy, because they're not gonna they're not gonna try to lose their resources on exploiting a hard vulnerability just because it's hard and it's no, they will just go after the lowest hanging fruits. The easiest way to attack a system is what's going to be the likeliest way that system is going to break. So I'm saying this because at the OS level, at the kernel, and at the user space, we see that there are a lot of primitives which indeed allows us to harden that environment. So what we have been observing is, because the OS environment is becoming more or less well secured, then the attackers are trying to subvert it. They're trying to attack lower. They're trying to attack the firmware, effectively, the early boot software, which, let's face it, firmware owns the system. Firmware is much more privileged than the operating system. It has access, for example, to the entire memory space of the OS and all the applications that run on top of it. And if an attacker is successful in exploiting a piece of firmware, then it actually allows them to be stealthy and to hide unnoticed by the operating system, simply because the operating system, for example, if it is scanning for potential attacks, it does not even have the ability to scan the firmware for that, because it is less privileged than the firmware. And the firmware is the one which controls the world view that it exposes to the operating system effectively. So it can be there and it can hide its own behavior from the operating system and the applications. And for that, it is very important that we think about how early boot looks like. I'm just going to highlight here a couple of of ways that we adopt at Ubuntu to achieve exactly that. So you would perhaps have heard of UEFI, and what it does is it allows the platform to only load as it is booting pieces of firmware that has been signed by a vendor that you have judged to be trusted. So for us, this is not specific to Ubuntu. The entire Linux OS ecosystem, they rely on shim to be able to sign then grub, which then also loads a signed kernel. And the shim is signed by Microsoft initially. So what we have here with Secure Boot is a chain in which a piece of software does not hand over execution to the next piece of software until it makes sure that it is signed and that it is signed by a key that is not revoked, for example, and that is part of the database of approved signing keys. So this at least gives you the guarantee that there is no extra malware that has inserted itself as the system was booting. You know you are booting into a known state. And that's way better than not having any boot security at all. Yeah, full disk encryption is another important primitive that we use, and its goal is to ensure that all data on the disk is inaccessible without the encryption key. We today the way we implement full disk encryption relies on passkeys. We have another implementation in progress. It's available as an experimental feature since 2 releases back of Ubuntu. And that one, the in progress implementation aims to have TPM, Trusted Platform Modules, TPM backed FDE. So this would be very useful eventually for enterprise customers who want to automate the use of full disk encryption at scale. And yeah, passkeys are not the most friendly in that regard. Okay, so I want to switch gears here to us trying to think about how we can defeat in this cybersecurity game. Not simply a particular external attacker, but sometimes we can be our own enemy because, especially for a large complex organization, operational complexity grows very fast. Um, and sometimes it is, I want to say natural, but it is not, it is expected that with complexity some things will fail. Maybe you will not have a good overview of all of the status or the security state of all your Ubuntu machines, or maybe, like many users that we speak to, you know that you have a vulnerability, like a kernel high or critical vulnerability that you need to patch, but you also have the business needs which conflict with the need for you to reboot the platform, because if it's a kernel CVE, you would need to reboot to patch it. But I don't know, maybe you are running a workload that requires some uptime, and you have SLAs that you need to meet. So you are suddenly confronted with the need to balance security and usability and business needs. So I really like this product because it takes a realistic view on how things are in the field. People have these conflicts all the time, and it gives us a very sophisticated answer to this problem. So Live Patch, it allows you to patch high and critical kernel vulnerabilities at runtime without requiring you to immediately reboot the platform. So you can continue to meet your SLAs for uptime. Uh, you cannot reboot forever. Like Live Patch does not take away the need for rebooting, but it gives you something very powerful. You have actually more than a year. You have exactly 13 months in which you would be able to apply live patches to your kernels without rebooting them. After 13 months, then we would expect you to reboot your platform in order to kind of restart the timer on another 13 months for non-reboots if you choose to do so. So in that sense, it's really saving a lot of cost because updates and reboots are expensive. They require They require IT hands on deck, and they require that that you cross your fingers and hope that things will come up as they were running before you rebooted. And they allow people simply to focus on running their core business versus drowning their IT resources on infrastructure maintenance that is not frankly necessary. Life patches, because they update the vulnerabilities at runtime, obviously they come with a slightly higher risk of regressions. Um, we do a lot of regression testing, that's not what I'm saying, but we are even a bit more careful because we allow life patches to be rolled in, let's call them in phases. You can define, for example, that these machines which are not running the highest, the most critical workloads will be consuming life patches first. And if you see that things have gone fine, then you would allow the life patch to flow through the other classes of platforms that you define, all the way up to your most critical workloads. We know that a lot of our enterprises are actually on-prem or air-gapped. They are running in air-gapped environments, and life patch can be consumed as well on those environments. It can be consumed as a SaaS. It can be deployed on-prem as air-gapped service. So another type of operational complexity is simply that it's not that you don't want to take the right security measure, is that you don't have the right overview over the things that are wrong or right in your estate. So you need a tool to give you estate management, not just one machine, but everything that you own basically. So for us, the answer comes in the form of Landscape. It is a truly outstanding system administration at scale, and it offers universal API for all versions of Ubuntu everywhere on any type of deployment, SaaS or on-prem in air-gapped environments. I'm just going to highlight here some of the cool features that Landscape offers. It can give you machine inventory. It can do software packages and repositories inventory. It can be used to distribute patches for the packages that you are already consuming. And you can use it also to configure and administer the proper identity management controls that you want to have. And it has alerts and monitoring capabilities as well. This is just to emphasize that if you are in an air-gapped environment, if you're in an air-gapped environment, you can still consume both Landscape and life patch effectively. Okay, so now we come into a truly determined attacker. So what I'm proposing here is a bit counterintuitive. So I'm going to ask you to think about a critical application that you are running. I don't know, a banking application, something like that. And I'm going to ask us to think about you running that application on a completely, you know that the host is malicious. I want you to assume that your operating system, your guest operating system, your hypervisor, your firmware, your host operating system, let's be crazy and assume they are malicious, they have vulnerabilities which are known, and you have chosen for some reason not to patch them. Is there a way that we can live in this world in which you can only trust your application and not trust everything else outside of it in terms of software, and still manage to preserve the integrity and confidentiality of your application's code and data? I know it's a very ambitious scenario, but I'm going to say it's not a new scenario, and it's not a crazy scenario, because let us think here about something that I trust that everybody is familiar with: SIM cards. What are SIM cards? SIM cards are simply very constrained execution environments. They have processors, they have some memory, they have some ROM, they are running some sort of operating system, and they are running some applications. And we have them on our phones. So what I'm asking here is why did telcos not run these workloads that are on the SIM card directly on the processors which are running on the mobile phones? Because supposedly those are much powerful processors. Like, what is driving them to go through the trouble of bootstrapping and acquiring this new execution environment just for the sake of it? It seems Well, actually not, because telco operators have been worried about the exact same things that I just described initially. They were worried that the mobile phone environments, the OS that runs on the operating on the main CPU of the mobile phone is not to be trusted. And the reason they have thought of this is because they know that privileged system software. So, for example, in this picture, you would be the user application and running in ring 3 as per the terminology of Intel x86. And privileged system software is everything that runs underneath you. So, kernel, hypervisor, system management mode, and we know that these things can be malicious because they can have vulnerabilities, but they can also be malicious because they can intentionally introduce backdoors. Some vendors can choose to hide backdoors into their software that they're distributing. So, because of this, it is not so unrealistic for telcos to assume that no, I care so much about the way that my user is going to connect back to the main network backbone. I don't want that application to be running on the this potentially malicious execution environment. And they understand, of course, that it is not enough that you, for example, encrypt the data of the application at rest with things like full disk encryption. Full disk encryption is great, but it is not enough. They understand that it is not enough that you have AppArmor confinement, or that you run in a hardened VM, or you have a FIPS compliant kernel for your guest OS. That's all fine, but for this type of determined attacker, this is not enough. The reason this is not enough is because let's think about the journey of data across its life cycle. So the data can be at rest, and yes, we have full disk encryption. At some point, let's say it is in your in some, I don't know. Let's say you are deploying your workload in a public cloud, and initially the data is in your on-prem machines. So it is at rest, it is safe, and you use full disk encryption, whatever. And then you decide to send it to the public cloud. You will still use encryption, and you will make sure that the encryption keys are stored securely in some hardware security modules. And then at some point in time, you would want to do something with that data. Like the reason you have data is usually because you want to derive value out of that data. So unless you want to keep your data encrypted forever, you cannot compute over ciphertext. So realistically, you have to bring data from rest, for example, from the hard disk. You should decrypt it first and bring it in clear text into system memory, into RAM. And that's what I refer to here as data in use, data at runtime. And that's at that point in time, when you are computing over your data, it is effectively up to grabs. It is available for the entire privileged system software to read it. The reason being, and I'm going to go some slides back here, is if you are running in user land, you are the least privileged piece of software on the platform. The OS, the kernel, they own you. They own you in the following way. They own you because they can read your memory unrestricted. Like, this is a design. I'm not describing here a vulnerability. This is just how computer works. They rely on abstraction layers and privilege layers. And kernel is responsible for managing your memory, for giving you the memory pages in RAM where you're going to run. But they also have access to your data and code. And if they choose to exploit it because they are malicious or because there is a vulnerability that is exploited, then when you are computing on your data, you are exposed to all of those vulnerabilities, and that's such a huge attack surface. So what am I saying here? I'm going back to my initial proposition. Can I protect my application from the same host environment that runs it? This is very important for public cloud providers. I think it's very obvious that we need it in public cloud deployments because we own nothing about the host. The hypervisor is not ours, the host OS is not ours. We're just a weak and privileged VM at best. If we are in a private data center, some people would tend to think that now they're fine because, well, it's my private data center. I chose the software. Yes, of course, you did that. It's slightly better than a public cloud deployment in that sense, but a private data center gives you governance. It does not give you security. A private data center, for example, would still be running the exact same software stack that the public cloud is running, and hence you have to worry about vulnerabilities in the kernel, and if you exploit it, your application is compromised. You know the story now. Also, because we know for a fact that many private cloud customers, they have multi-tenancy requirements. I know that a lot of telcos, they choose to actually act like a mini public cloud provider. Some media companies would want to consume resources, compute resources from somebody who is closer to them or within the same jurisdiction. Whatever the case is, there are multi-tenancy requirements even within the one private data center deployment. And as I mentioned, we have the same software vulnerabilities, and you also have insiders that you cannot realistically vouch for every one of them that they are going to act as they should, and they're not going to turn malicious for whatever reason, because they're paid or because they're angry, or yeah. So what is the solution here? Am I advocating that we revert back to using SIM cards on servers and that everybody should have a SIM card to run their workload, the one workload they worry about? That would be a solution, but it would be a very, very unpractical solution. But no, not what I'm proposing. What I'm proposing has come to become known as confidential computing. And in a nutshell, I'm going to be very high level here, is confidential computing technologies are implemented thanks to silicon companies. And those silicon companies have put hardware encryption engine within the CPUs, within modern CPUs. And those encryption engine are capable of encrypting at runtime your memory pages. So I'm not talking here about full disk encryption. Full disk encryption is for hard disks. This is for RAM. As you are running, your RAM, your DRAM is encrypted. Every time you write, it gets encrypted. Every time you read a memory page, it is only decrypted within the CPU. So what this means is very powerful. It means, yes, you can have an OS which has a vulnerability. Somebody will try to exploit that vulnerability, and maybe they will be successful, for example, in dumping the memory of your VM, but all they will see is ciphertext. Because, well, the encryption key is stored in hardware, they cannot reach it. And ciphertext, if we trust that AES is unbroken because these memory encryption engines are AES engines, then we're fine. There are many other details around this technology, and we have other webinars and materials in which we go into further details about them. But for the sake of this webinar, I think it's enough that we are aware that there is indeed, for you as an Ubuntu user, a primitive to protect yourself against the entire software stack that runs underneath you. And by using confidential computing at the VM level, for example, if you choose to deploy into an Ubuntu confidential VM, what you will have is effectively removed millions lines of code from the attack surface, because suddenly the firmware hypervisor, you don't have to worry about them anymore. I would like you please to know that you can easily get started with this technology if you want to experiment with it for your private cloud. We have, for example, TDX is the Intel's technology for confidential computing. On this repository here, I don't think you cannot access it. I should have put a QR code or something, but you can type canonical Ubuntu Intel TDX, and you can hit the GitHub repo which come up first, and you will find there available for you all the software pieces to just get started and build your confidential private data center from the host all the way to the guests. We provide host OS patches, kernel, KMU, libvirt, and then OVMF as well. But if you want to start light of your public cloud is generally your target deployment mode, then please go on any one of those major public cloud providers and you type Ubuntu confidential VMs. Use them, start using them. And actually, I hope you don't notice that they are much different than your normal Ubuntus, because that's what our job has been in the past few years, to take away the complexity of confidential computing so that it just works once you choose a VM with that feature. If you are interested in confidential computing because you have specifically AI needs that require GPUs, and what I described here is only CPU technology, then I'm really happy to share that we have that capability. We have been the first Linux operating system to offer confidential AI, for example, on Azure. And effectively, this is made possible thanks to NVIDIA H100 GPUs, which allow you to extend the execution environment from the CPU from the CPU all the way to the GPU. There is some attestation flows which need to happen. We have write-ups about how that should look like on our Canonical blog website, so please do consult those, or you can simply go to our confidential computing webpage and do use the contact form. We read them and we get back to people who ask us questions about either the use case or how they can use it. You can also email me directly if I will leave my contacts on somewhere on where you are watching the presentation. So yes, again, if you are an AI user, confidential AI is possible with GPU capabilities. We work very closely with NVIDIA on making that possible. These are just some of the resources you can go back to after this webinar. There is deployment guide for you to make confidential AI work with Ubuntu 24.04 and Intel TDX. On the public cloud, we are available both on Azure and Google Cloud. And this is a particularly useful deployment mode that I have found to be pretty popular with a lot of enterprises who are looking into LLMs. They want to deploy RAG. Forgot what it stands for. It's something augmented. Yeah, I just use RAG, and that's how it is now. It's not abbreviation anymore. It's just RAG. So you would know what I mean. It's for confidential RAG. I particularly like this use case because, yes, of course, it is a complex use case to deploy because you need a confidential VM, and within a confidential VM, we need to be able to deploy the RAG setting itself. And to deploy RAG, you need a vector database. You need potentially something like Kubeflow, and you need a model. And Canonical offers all of that. So I like the fact that we are able to offer RAG as an integrated offering from the infrastructure all the way up to the applications, because things usually break at the interface. And yeah, it's just nicer to consume from the same vendor who is not going to lock you down, but still the same vendor who is going to do thorough testing to make sure things just work across the entire deployments as they should. And I really like, it's not my product, but I do enjoy a lot working with Charmed Kubeflow and with Charmed OpenSearch. I invite you to take a look at them after the webinar if you are into LLMs, and they're very easy to use even if you're not an expert. So that's why I enjoy them, I guess. I think that brings us to this slide where we see an overview of the game that we've been playing with the supposed attackers. We started with just somebody who is going to exploit a known vulnerability for which an exploit is available. And then we finished with an attacker who is controlling the entire host platform on which you are running. And we have been able to see what are the security primitives available to you as an Ubuntu user to defend against each one of those classes of attackers. It is up to everybody to study and to think about the risk that they want to take. Not the risk they want to take, but the risk versus the cost for mitigating that risk that makes sense for themselves as a personal user, for their organization as a business. And we leave that exercise up to everybody to do. But wherever you land on this scale, you have a primitive to accompany you as an Ubuntu user. And here we are. I really hope that you can see by now that the Ubuntu security offering have a lot of thought put behind them. It is not just a collection of tools that we throw on the way of our users. They are an ecosystem of layered defenses, and each one of them is very carefully tuned to address specific threat levels and attacker capabilities. And yeah, we hope that when you understand the nuances of what each primitive means, you'll be better equipped to make the best decisions for yourselves. This is a fun game. Cybersecurity is fun. I'm in this field because it is fun. It requires you to be a bit imaginative, to be 2 steps ahead. Some of you will pick up on if some of you are watching YouTube too much, you will know this reference. 2 steps ahead. Yes, we are in that kind of mindset, and it is a game also. So let's play. It's up to you to decide what's your gameplay. I still have a few minutes left on the webinar. I would like to go over some of the questions. I see I have here comments, questions. So let me go through them. By the way, if I don't get the time to answer all of them here, I will. Yeah, well, I don't have your contacts, but if you left them on LinkedIn or something, I will just answer under your comments. If you have a perfect way to distribute the one-time pass keys, just use 100%. Indeed, that's why that's ridiculously unusable. It is impossible to adopt a one-time pad in practice. I do know, however, that there are very niche use cases in which people go through the trouble of replicating a one-time pad like algorithm. I think, for example, for the aviation, not like when you go through a passport control, you give them the passport, and then your passport actually has a chip that talks to something in order to do some key actions, blah blah blah. And every country has a root key. I think I attended a presentation in which it was shared with us that countries, they do meet physically every now and then in order to make sure they are exchanging with each other physically the keys. So in that sense, they can go away the problem of key distribution because the use case warrants that they deploy all of that efforts. But clearly, this is not something that we can build, that we could have built the internet on. Yeah, I see a 5% comment. I think that's in reference to how many people have patched their vulnerabilities after 2 months. You are a bit more pessimistic than I would have thought. I was expecting people to say now it's just like 60 or 70%, but no, it's 25%. Not good, but yeah. To implement the several, does Ubuntu include tools to implement the several CIS or other standard? CIS and Disaster, yes. Please look for Ubuntu Security Guide, USG. It's a tool. I know the name is confusing. We're working on that, but it's a tool specifically to audit and to implement, if you want to call it that way. I was referring to it as to remediate, but yes, you can apply the hardening profiles that you choose for your platform. Yeah. Since CIS hardening, somebody was asking about CIS hardening for 2404. It's going to be slow coming. I don't think that there is something in the interim that I can offer. I can ask, it's not my main focus, CIS hardening, but I can ask a colleague, and if the answer is not, if no is not the answer, I would comment on wherever you left that question. Our libraries live patch in memory, glibcs. The only live patch we apply is, for now, is kernel. It's if it's a kernel vulnerability, and not all of vulnerabilities, if it is a high and critical. The reason we don't live patch everything, even if we could, is just because we know